We're going to do a little more here with simplifying radicals. In other words, simplifying something like the square root of 125. But before we get there, I want to share with you kind of a conceptual of what we're doing. You know, when you studied fractions and you had an answer to a problem of 2 over 4, and you were required to reduce that to 1 over half. So I was reducing the fraction, and this is the proper answer. That's the same kind of thing that we're doing with radicals, is we're reducing it and giving the proper answer, the reduced form of the answer when we simplify radicals. Before we're able to do that, what I want to do is I want to list for you a list of what's called the perfect squares, because we use these to help ourselves simplify radicals. So perfect squares are numbers like the number 1, the number 4, the number 9, the number 16, the number 25. Because every one of these, if you take the square root of them, you get an integer answer. So the square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. And remember that the way I can come up with these, in case I don't know what the next value is, which is 36, is I can think of the answer 2 here and square it, and that will give me the perfect square of 4. And therefore, the square root of 4 is 2, because 2 times itself gives us 4. Even 1. You know, 1 squared is 1. 3 squared is 9. 4 squared is 16. 5 squared is 25. And so you need to become familiar with this list of perfect squares, you know, pretty well up into at least through 100. 121 would be the next. 144, 12 squared is 144. So be familiar with those. Then, in order to simplify a radical, what you have to do is you have to break the number 125 into the product of two numbers. And you have to look for the number in this list that divides into 125 evenly. And you got to look for the biggest number in the list that divides into 125. And if you took your calculator, 125 divided by 25 would be 5. And so now what you could do is you can take this right here and simplify it, because you know the square root of 25 is 5. Bring down your square root of 5, and this is the reduced form, or the simplified form of the given problem, the square root of 125. It's more proper to see it like this. So let's continue to do a few more. You might, as I give you some options in terms of problems to do, you might go ahead and, I'm going to go ahead and number these. You might go ahead and stop the video and try it yourself. So here's the next one I'd like you to try. So look for, and you need to look for the biggest number in this list. Yes, 4 goes into 300. And yes, 25 goes into 300 about 12 times. But the biggest number that goes into 300 in this list is the number 100. In a minute, I'll show you a problem where you can get at it by using not the largest number, but it's so much easier if you would break this up into the product of two numbers and use the largest number in order to reduce this. Because 100 times 3 is 300, and the square root of 100 is 10. So 10 times the square root of 3 is the reduced form. The next problem I'd like to show you, I'm going to do it two ways, in case you didn't notice. So the square root of 72 is the problem that we're going to do. So sometimes the first thing that comes to people's minds is 9 times 8 is 72. And it is. It's true. And 9 is in the list, way back up here. 9 is in the list of perfect squares. So you could go that way, and the square root of 9 is the number 3. Whatever you do, a lot of people, for some reason, I'm not sure why, when they reduce the square root of 9, they leave a square root symbol over the 3. The square root of 9 is just the number 3. Don't leave that square root symbol over it, times the square root of 8. But you've got a problem. The square root of 8 is not reduced totally. So the square root of 8 can be thought of as the square root of 4 times the square root of 2, because 4 times 2 is 8. Remember, this is 3 times. There's a dot right here. 3 times the square root of 8. 3 times the square root of 4. So 3 times the square root of 4, which is 2, is 3 times 2. I'll bring that square root of 2 down. So finally, we're done after how many steps? Too many. So what would have been better for this square root of 72 is to notice that a 36 is in the list of perfect squares. 36 goes into 72 2 times. The square root of 36 is 6. And then you bring down that square root of 2. And you got the same answer, but look at how much shorter it was to do the problem. So if you would try your best, and if you can't, you got to pause and look at the number that's under the radical and say, is there another perfect square that will divide into that? And then you'll always be right. So better to go biggest first, but if you don't notice it, then go ahead and simplify again. So let's see, I think this is our 4th question. So this problem that I'd like to do next is 3 times the square root of 36. Well, aha, square root of 36 is a nice number. It's just 6. So this is just 3 times 6, or 18. Let's see, let's try another. So now let's keep a coefficient in front, but now this time, instead of the square root of 36, let's put a number under the radical that is not a perfect square. So what number divides into 40? That's in the list. Remember, the list includes, I like to start with just 4, and then 9, and 16, and 25. So I kind of keep this list, and if I were you, I'd just go ahead and write it on scrap paper as soon as I receive my test. I'd write this list down. So I know 4 goes into 40, and if I, don't forget the minus 5, if I have 4 go into 40, it goes in there 10 times, and 10 doesn't have a number in this list that divides into it, so I know I picked the right number. So I have a minus 5 here times the square root of 4 is 2. So right there, the square root of 4 is 2. And a minus 5 times 2 is a minus 10 times, bring down that square root of 10. And I have simplified this radical. All right, here's our next one. The square root of 245 divided by 16. When you have a quotient under a radical, I just want you to know that you're allowed to break that up into individual radicals, so that in the denominator you could take that 4 out of the square root of 16 and call that 4. However, it's a real tough one to see, but the square root of 245 is divisible by 49. And I believe 49, if you take your calculator and go 245 divided by 49, I know it's an odd one to notice, but it goes in there 5 times. And then in the denominator, you have the square root of 16. So finally, I'm going to write my answer here. The square root of 49 is 7. I've got the square root of 5 next to it. Downstairs, the square root of 16 is 4. I can leave it just like this. That's fine. There's multiple ways to write it. You could write 7/4 times the square root of 5, but kind of keep that square root of 5 up higher because it can't be thought of as though it's in the denominator. All right, so in that same light, that same vein, so if I give you the square root of 2 over 121, just want you to know that you can break that up. Square root of 2 over the square root of 121. Upstairs, nothing you can do with that. Downstairs, square root of 11 is 121. Next, and I'm just going to try to make these a little bit more challenging each time, I've got the square root of 12 over 196 with a negative sign out in front. Don't lose that negative sign. In the numerator, I've got to think of 12 as 4 times 3. And the square root of 196, I believe, if you check it on your calculator, is just the number 14. The square root of 4 here in the numerator, now I've got to call it 2. Don't forget that square root of 3 over 14. Don't forget your negative sign. You can put it in front of the 2, you can put it in front of the fraction bar, you really can put it anywhere. But now, do you see this 2 and this 14? They are outside of a radical. They're just like a fraction. I'm just going to come out over here so you can see it. They're just like this fraction. So you have to go here and say that 2 goes into here once and into here 7 times. So you've got your finished answer as a negative 1 times the square root of 3 over 7, or just a negative square root of 3 over 7. That 1 doesn't necessarily have to be written there, and actually I wonder if my math lab would understand it. I hope it would. That's a pretty simple thing for my math lab to understand. Okay, so let's deal with some letters. I'm going to come on over here. We've dealt with the square root of x to the 8th is x to the 4th because the index for a square root is a 2. And we said there's this fractional exponent rule that allows us to take that 8 divided by 2 and give us x to the 4th. Plus, we know x to the 4th times x to the 4th would give us x to the 8th. But what happens when the number underneath the radical is odd? Like a 7, and I want to take the square root of it. What I'm going to do is I'm going to break this up into x to the 6th times x to the 1st, because when I add their exponents, it adds to be the 7. And the square root of x to the 6th, I'm going to write this for a little bit until you get used to it. I can write that as a fractional exponent. 6 divided by 2 is the fastest way to think through that. That's x cubed. Bring your square root of x down. You've got to bring your square root of x down. It's x to the 1st power. It cannot be reduced. Let's do another one. So we've got the square root of 49a to the 5th power. So I'm going to break this up into 49, a to the 4th, and a to the 1st. So the square root of 49 we know is just the number 7. Again, please don't put the radical symbol on it. The square root of a to the 4th, 4 divided by 2 is 2. And then this square root of a has just got to come down. Cannot be reduced. Next question. Square root of 18 over m to the 10th power. The m to the 10th is nice, but the square root of 18 has got to be reduced. I've got to think of it as 9 times 2. And now let's go ahead and pull everything out that we can. So the square root of 9 is the number 3. The square root of m to the 10th, that's supposed to be a 2 here as the index. 10 divided by 2 is 5, and I'm done. So let's do something similar again with an odd exponent and a number that's got to be reduced. So the 12 here is going to have to be reduced, and the m to the 11th will have to be reduced. So let's break it up into a bunch of parts. Let's break the 12 up into 4 times 3. Let's break the m to the 11th up into m to the 10th times n to the 1st. I don't know if you've noticed this, but this was an m to the 11th. So when it's square roots, you go to the even number right below the odd, right below this 11. So the number right below the 11 is 10. And 10 will be divisible by 2. That will become m to the 5th. That's how you make your choices for square roots. So here, the square root of 4 is 2. What I like to do sometimes is I like to cross this off when I've dealt with it. So the square root of 4 is 2. The square root of m to the 10th is m to the 5th. And then see this square root of 3 and this m? It's got to stay under a radical. This video is getting a little bit long, but I've only got a few more problems I'd like to share with you. So this next one, the square root of 21 y to the 3rd over 100 x to the 12th. So 21, nothing I'm going to be able to do with it. Y to the 3rd, I'm going to think of as y to the 2nd and y to the 1st. Downstairs, square root of 100 is 10. Square root of x to the 12th is going to be x to the 6th. So let's go ahead now. Square root of 21 and the y, I can't do anything. But the square root of y squared is just the letter y. And then the 21y stays underneath. Downstairs, the square root of 100 is 10. The square root of x to the 12th is x to the 6th. And I'm all done. All right, let's talk about cubes real quick. Perfect cubes. So the list of perfect cubes includes the number 8 and the number 27 and the number 64. These are hard to memorize, so I just produce them by taking integers, 2 cubed and getting 8, 3 cubed and getting 27, 4 cubed and getting 64. So if I want to find the cubed root of 72, I have to find a number in this list that divides into 72, and the only number is the number 8. And 8 times 9 is 72. The cubed root of 8 is the number 2, because 2 times 2 times 2 gives you 8. Be careful, the cubed root of 9 is nothing. It's not the square root of 9, it's the cubed root of 9. You got to leave that. Finally, my last example, the cubed root of 11 divided by 8. I'm just going to think of as the cubed root of 11 over the cubed root of 8, and the cubed root of 8 is the number 2. Can't do anything with the cubed root of 11, and I'm all set.